Hello everyone, and once again welcome you all to the course on kinematics and theory of machine. So in the previous lectures we have already discussed about inversion of four-bar chain. There we have seen the four inversions and their applications. Like the first inversion application is throttle build up locomotive. Then in the second inversion we have discussed about beam engine. Third inversion about pantograph we have already discussed. In the fourth inversion what mechanism we have discussed. And similarly later on we have discussed about the inversions of slider chain. Here also we have discussed all four inversions. So in the first inversions we have seen how reciprocating engine as well as reciprocating compressor can be obtained. Similarly in the second inversion we have discussed about the Whitworth quick return mechanism and the rotary engines, which are basically used in the Sapper machine in your workshop as well as in the light aircrafts, etc. So those things we have discussed. Similarly in the third inversions about oscillating cylinder engine as well as crank and slotted lever quick return motion mechanism, those things we have already discussed. And later on in the fourth inversion we have discussed about the application of hand pump. So today in this lectures we are going to discuss about the inversion of double slider crank chain. So here basically from this double slider crank chain we are going to get three main inversions which will be useful. The first inversion of this double slider crank chain is our elliptical trammel. So what is this elliptical trammel? So basically it's an instrument which is used for drawing ellipses. Okay, so that means drawing ellipses means you can either drawing ellipse or by the person which is going to trace ellipse, you can have some other part there and you can have a movement of that particular part in the form of an ellipse. Okay, so now in this particular case what basically happens, this inversion is obtained by fixing the slotted plate. Here in this particular figure this is nothing but that particular slotted plate. Okay, so number 4 link. Okay, or you can say in this particular GIF this is this particular plate which is being fixed. Okay, now this particular slotted plate, what is the, you can say, uniqueness? So this particular slotted plate, it has got two straight grooves. Okay, orthogonal straight grooves. Orthogonal means 90 degree to each other, which are cut on it. Okay, so they are 90 degree to each other and they are like the groove. Okay, so it's there is the groove. Okay, and in this particular groove, okay, two sliders. So here link 1 and this link 3. So in this particular they have the yellow portions. Okay, both the yellow portions. Okay, so they are nothing but this particular sliders. Okay, so link 1 and link 3, okay, which are nothing but the sliders and forms sliding pair with link 4. This is the plate. Okay, so as this you can see from the GF, so basically this link 1 and link 3, which are nothing but the slider, during the course of its motion it is basically sliding with respect to this, they are having sliding motion with respect to base 4. Okay, so base 4 was plate was link 4. Okay, and this particular one bar you can see. Okay, so this particular bar, so basically the link AB, which is here AB. Okay, so this link AB is in the form of a bar and it forms turning pair with link A, link 1 and link 2. That means along with this particular slider you can see pin joints are there in the bar and in the particular slider. Okay, so basically it can have turning, it is basically forming turning pair with the slider 1 and 3. And as from the very both the GFs you can very easily see when the link 1 and link 3 slides along their groups, respective group, any point on the link 2 is that particular bar. Okay, point on the link 2, such as we have considered a point C here, for later on we'll see for analysis purpose. So any point on it traces an ellipse on the surface of link 4. Okay, so this is how basically you should remember that it is basically going to get this kind of elliptical movement there. Okay, so I think from the GIF it is very evident. So next we are going to see whether actually they are going to form a elliptical movement or not. That means the whatever equation of motion that we get, or that for that particular using that particular location points. Okay, so it should have, we should get an equation for ellipse, then you can say that the movement is basically elliptical. So the analysis is very easy. So in this particular figure link 2, that is the bar, it is making an angle theta with the x-axis. Okay, we are considering we are considering semi minor axis as the BC, and which is equal to A we have considered. So here to here that BC was there, okay, C was the point on it, okay, and that is semi minor axis. This particular bar is making angle theta. This angle is theta with x-axis, okay. Similarly, semi major axis is equal to that C up to that particular point, okay. So C, and which is equal to small b we have considered, okay. And if you can see, so the coordinate of that particular point C, which is located on the bar AB, we have considered as x comma y, okay. So x comma y means, so along this direction this mass is x, so this is the origin, okay, this is the origin point. So from here to here this mass is x, that means, and this length is y. So now from this particular, this what we can write that x equal to BC, this is x, okay, x equal to this particular BC, and this angle is theta, BC cos of theta is going to give you x equal to BC cos of theta, okay. So from here we can write x by BC equal to cos of theta, okay. Now what is BC? BC we have already considered as equal to A, so x by A equal to cos of theta. Similarly, about y, this particular length, what we can write, this y equal to, we can write, so from here to here this is y. If we consider this mass, angle is theta, and this length is basically your AC. This is A point, that the other point was C. AC, I can write y equal to AC cos of theta, not cos of theta, it should be sine of theta, because we are talking about the y, okay. So from here what we can write, y by AC equal to sine theta. So from there, AC already we have considered as B, so these two we have now as equals 1 and 2. So if we square and add, x square by a square plus y square by b square is equal to sine square theta plus cos square theta, and that is nothing but sine square theta plus cos square theta is nothing but 1. Yes or no? We already know sine square theta plus cos square theta equal to 1, so directly we have put as 1. So now from here what we can say, this we have obtained an equation of ellipse, okay. X square by square plus y square by b square equal to 1. So now we already know this circle, it's a special form of, we can consider as a special form of ellipse where semi major axis and semi minor axis both are same, that is this A equal to B in that, in case of our circle, okay. So now let's consider that equal to that AC, that is this mass AC, and you can say this BC equal to, they are same and equal to the radius of the circle R, okay. So in that particular case what we can write, x square by this is A is nothing but your A square, and this particular thing you can write x square plus s square plus y square by bc square equal to 1. So from there, AC equal to BC equal to the radius we have considered, so we can write x square plus y square equal to r square, which is the equation of the circle. So for center midpoint of AB, it becomes a circle, okay. So it is going to trace a circle. We have also obtained this equation, okay. So this is about elliptical triangle. So next inversion is second inversion, we obtain Scotch mechanism. So what happens here, so in this particular Scotch mechanism, so we are basically going to use it to convert rotary motion into sliding or reciprocating motion, okay. So now here the link 4 is in the form of in the shape of a T, okay, and this is link 1, and this crank, which is actually crank, it is link 2, okay, and it is connected to a slider which is there on the T, okay, which the whole T is this T portion is the link 4, okay. This is link 1, and this is link 2, the slider is link 3, and this guide is once again link 1 only, okay, that is fixed. So now these are the 4 links. So now as the link crank 2 rotates, the horizontal portion of the link 4, it, that is this particular crank, okay, the crank rotates, the horizontal portion of the link 4 slides in the fixed link 1. So it can slide like this, as it is evident from this particular GA. Okay, you can see this blue portion, that is nothing but the slider. Okay, and this particular T portion, that is the red. Okay, here this portion, the vertical portion, we have to put the slot there. Okay, so now in that particular there only this slider is inserted there, the blue part. Okay, which is connected to that particular crank. Now when the crank moves, so the slider slides along this particular direction also, and as the crank is moving like this, so in that particular case, along with it reciprocates the T, this horizontal portion of that particular T in this particular case. Okay, so rotary motion of the crank has been converted to the reciprocating motion here. So wherever we record this kind of movement, that means we can use this. Okay, so very easily you can say link 2, that is the crank, it makes two turning pairs, one with your link 3, that is this particular one here and one here in this particular link. Similarly, link 4, that is the sliding. Okay, link 4 makes two sliding pair, this 4, one with this particular guide 1, okay, and another with this particular slider. Okay, next the third inversion, which is one of the very widely used inversion, and the application is we got the Oldhams coupling from the third inversion of double slider crankshaft. Now, where these Oldhams couplings are used, we already know these couplings, they are used to connect something. Okay, and most of the cases two shafts we connect with the help of certain couplings. Okay, now in case of this Oldhams coupling, what is the specific use of this coupling? Why it is very much we are interested in studying this? So basically, these Oldhams couplings are used to connect two parallel shafts whose axes are actually at a small distance apart. They are having certain eccentricity. Okay, so basically two shafts, if we are talking about this particular shaft and this particular shaft, which is having some eccentricity between them. Okay, but they are parallel, but they are is at a small distance apart. Okay, they are not in the same line. Okay, but if one is here, another is somewhere here. They are parallel but at a particular distance apart. So for connecting this kind of two shafts, okay, we use this particular Oldhams coupling. So now with the application of this Oldhams coupling, what happens? Whatever be the, if we connect with the Oldhams coupling, okay, when one of the shaft rotates, the other shaft also will rotate with the same speed. Okay, and that is what we want. Okay, we want that there should not be any loss in the movement. Okay, loss in motion. So basically, whatever, if omega is the velocity, angular velocity at the driving side, so in the driven side also, after the coupling, okay, it should be omega only. Okay, and now if we discuss with respect to this particular figure, then how can we obtain this particular thing? So basically there are two flanges, flange part, one is this, another flange is this. Okay, and this first flanges we have numbered as link 1. Okay, and then this has been this other flange number 3rd. Okay, and to connect these two flanges, basically we have an intermediate piece in between, special design that we will see, and that has been numbered with link number 4, and we have this particular supporting frame, link number 2. Now in this particular case, whenever we fix this particular supporting frame, that is the link 2, we basically get this particular Oldhams coupling. Okay, and now in this particular case, link 1 and link 3, that is that of both the flange parts, they form turning pairs with link 2, that is the supporting frame. Okay, and now what about this particular flange? Okay, and how they are basically connected is that I have said that there are certain specific style in this particular flange. So now this is one face of this particular flange. Okay, this is another flange, and this flange. Okay, and they are being connected. And how they are connected? So basically they are connected with another intermediate piece, and both the intermediate piece as well as the face of this particular both flange, okay, they are having certain design modification so as to accommodate or so as to connect. So what basically happens? So here this is the intermediate link, okay, link 4. Okay, so now what basically happens, the flanges, these two flanges, this and this, okay, it has got diametrical slots cut in their inner face. Okay, so this side for this case, okay, in this side face, similarly for this side flange, okay, in this side, okay, basically the inner face is this, and this face and this face becomes the inner face. Okay, so basically diametrical slots are being cut. Okay, and now this intermediate piece which is connecting both the faces of the flange, okay, basically they are connecting both the flange. Okay, so what happens now, this intermediate piece which is link 4, which is once again a kind of circular disc only, it has got two tongues. Okay, and that is along that particular corresponding to the diametrical slots, it has got two tongues. Tongues mean that projection. Okay, that means it is moving, it is like you can say something is which is bulging outwards. Okay, so you can say this T1 and T2 in the other side, diametrical side. Okay, so they are the two tongues, and these are kind of outward projections. So in the slot which are being cut here and here, first flange and second flange in the inner side. Okay, so these two tongues, that is a diametrical projection, it will be inserted, and thus it connects both the sides. Okay, and they are at right angles to each other. Now the tongues on the link for this intermediate link is closely fit into the slots which are there in both the flanges, first side and second side. So here you can say one flange is this intermediate link, we have another flange is this. So they are connected with this particular circular disc, okay, having this kind of projection, outward projection, and in the flange side we have got the slots. Okay, and this particular link, that is the intermediate link, it can slide or reciprocate in the slots in the flanges. So it will be very evident once you see the GIF. So now here in this particular animation, you can very easily see that this is one shaft and this blue portion is another shaft which we want to connect with the help of what? With the help of this Oldhams coupling. We can very easily see if we like this. Okay, so both the axes, they are not coinciding, okay, not concentric, so but they are having certain small eccentricity between them. So in these kind of cases, basically this particular Oldhams coupling we are going to use. Okay, so now in case of this Oldhams coupling, what you can very easily see, basically this is the one flange part, the blue part is another flange part, and this green is the intermediate link which connects both the flanges. Okay, and from the there you can very easily see there is one this particular slot cut on the right side. Okay, similarly there is another slot, okay, in the blue side. Okay, and if you can visualize from the particular green plate, okay, which is the intermediate plane, you can see that so some extra portions which it is coming out, okay, from that blue part. It will be evident here once it reaches this side. Yes, now you can see, yes, once extra thing it is coming out, okay, that tongues are coming out. So along with that, with this particular part, with this particular sliding, basically it is connected. Okay, and now the midpoint of the intermediate piece, it describes a circle with distance between the axis of the shaft as the diameter, very evident. The maximum velocity how can obtain, the maximum sliding velocity of each tongue in the slot, which is the peripheral velocity of the midpoint of the intermediate disc, we can obtain as the maximum sliding velocity equal to the peripheral velocity along the circular path, which is equal to the angular velocity of the shaft. Okay, it's just like V equal to omega r, or V equal to r omega, which we already know. So this is another something like one expression only. So this is how basically the Oldhams coupling used, and why this works, and why these Oldham couplings are being used. So it is used to connect two parallel shafts which are at a small distance apart. Okay, so in the next lectures we'll be discussing about one of the interesting motion mechanism, that is the straight line motion mechanism. So there we'll discuss about exact straight line motion mechanism and approximate straight line motion mechanism. if you can recall, already we have discussed one of the approximate straight line motion mechanism, that is the watt mechanism. We have already seen as the as one of the inversion of slider crane mechanism, or not slider crane mechanism, the four-bar mechanism. Okay, so for today we stop here and hope you like it. Thank you.